In this module, we'll go over optimization methods that take CPU cache into account. As processor speeds have exceeded RAM access speeds in the past decade or two, the use of fast on-chip CPU cache has become essential to full CPU efficiency. We won't explore all the architectural issues surrounding cache in this module, but we will introduce a simple example of the most common cache architecture, and then look at standard approaches for optimizing with respect to cache usage and tools for profiling cache use. Now, cache memory is a small amount of very fast memory that resides on chip with the CPU. The CPU keeps the content of the most recently or most commonly used memory addresses in its cache and reads and writes them there at a much higher speed than would be possible from RAM. Now, if a given memory address is read in multiple times in a short period, then the CPU must read it once from RAM slowly, and then it can read it repeatedly very quickly from cache. And it can write to cache as well. Any write into cache must also be written out to RAM for permanent storage, either immediately or perhaps after some delay, depending on cache design. But the CPU doesn't need to wait for the slow write to RAM to complete, because an accurate copy of the new value will be in the cache to be read immediately. Now, a typical CPU as of this writing offers perhaps 64 kilobytes of fast cache, serving a memory of perhaps 6 gigabytes. Those are pretty big values to draw and discuss, so we'll use a smaller model as our example case. Let's call it the minimum model. Now, the minimum model is fully representative of realistic caches. It's just a matter of scaling it up and adding more bits to the addresses. So here's the minimum model, as shown in the diagram here, and it has all of 4096, 4 kilobytes of RAM. Don't laugh, that was a realistic figure maybe 40 years ago. The CPU has a small, fast cache memory, and that one is 128 bytes. Now, how exactly is RAM content stored in the cache? One might imagine some sort of general lookup table where a given memory address and its associated content would go into the cache as a key value pair in a map or a dictionary. The CPU would attempt to look up a desired address in the cache before resorting to RAM. Now, such an arrangement is possible, and it's called a fully associative cache. But it's hardware expensive and/or it's slow to look up addresses in a large associative table, so this design is not common. Instead, a typical cache is organized in groups of bytes called cache lines, with specific areas of RAM devoted or assigned to specific cache lines in the cache. A cache line is larger than a memory word, typically large enough to store several memory words. Our minimum model will have 16-byte cache lines. So, just kind of to warm up here, question number 1, how many cache lines are there then in the minimum cache? No tricks here. It's a fairly straightforward answer. It's just an are you awake question. Given 128 bytes of cache and 16-byte cache lines, we'll have 8 cache lines, right? And I'll draw that here and tighten the diagram up a little bit while we're at it. Now, a realistic cache might have maybe 2K or 4K, 4096, cache lines of 16 or perhaps 32 or maybe even 64 bytes. Now, we've got a drawing here then with our cache having just 8 cache lines of 16 bytes each. Now, RAM doesn't get copied into the cache byte by byte. It's copied a cache line at a time in 16-byte blocks the size of a cache line. Each cache line sized piece of RAM is called a cache block, and the RAM cache blocks are on 16-byte boundaries within the RAM. One cannot, for instance, copy addresses 8 through 23 from RAM into a cache line. It would have to be addresses 0 through 15 or 16 through 31, etc. Now, given this, we can view our RAM as broken into 4096 divided by 16, that's 256, cache blocks. I'll draw the first 16 of those and the last 8 with some ellipses in between. Now, this does not imply, by the way, that machine instructions can fetch RAM only by entire cache blocks. An instruction might still request, say, 4 bytes starting at address 8. But if it does, the entire 16-byte cache block that contains that value goes into the cache, whether you're going to use the other 12 bytes or not. Very often you will use the other bytes, since it's common to fetch adjacent memory words, but it's not guaranteed. So, can any cache block from RAM go into any cache line in the cache? No. There's a further restriction. For simplicity of hardware, each cache block in RAM has one and only one home cache line, that's not an official term by the way, in the cache. It doesn't go into any other cache line but that one. The first 8 cache blocks in RAM go to the first 8 lines in cache, one by one, as their home cache lines, as the diagram will show here. If they're cached, that's where they'll go. Now, of course, there are a lot more cache blocks than cache lines, so many cache blocks must share the same cache line. The next 8 cache blocks in RAM also have the same home cache lines. Again, as shown in the diagram, and I'm going to declutter it a little bit here. And that pattern continues all the way through the RAM, with home cache lines rotated over and over again so that every 8th cache block goes into the same home cache line. And more accurately, they'll compete for the same home cache line, since only one cache block at a time can occupy the cache line. The rotational pattern at least ensures that nearby cache blocks won't compete for the same cache lines, but it doesn't prevent competition between widely separated cache blocks. Now add in the last 8 cache blocks of RAM there too to the diagram. Now, the 2 biggest jobs in optimizing for cache are to focus on small groups of data at a time, so that what you're working on will fit in cache, and to structure your data to minimize competition for home cache lines. Now, here's a few questions to be sure you've got all this straight so far. First, a simple warm-up question. In the minimum model, how many cache blocks does each cache line serve? How many cache blocks, in other words, compete for the same cache line? Say perhaps that one. Coming back from a pause there, the 4096 byte RAM has 4096 divided by 16 is 256 cache blocks, as we said earlier. Every 8th one competes for the same home cache line, so there are 32 cache blocks, 256 divided by 8, competing for each home cache line. So, question 3. What bits do the addresses of the 16 bytes in a cache line, or a cache block, have in common? What bits would differ between them? And coming back from a pause, given that a cache block starts on a 16-byte boundary and is 16 bytes long, only the bottom 4 bits in the addresses of its bytes will vary. The top 8 bits will be unchanging within the same cache block. For instance, bytes 64 through 95, which I'm actually pointing to right there, form a cache block. And their addresses would be, their addresses are 0000, 0010, and then 4 zeros through that same 8 bits and 4 ones. We might say that the top 8 bits of the address identify the cache block, and the bottom 4 bits indicate the byte within the cache block. Question 4. The first 8 cache blocks in RAM all have different home cache lines. What do all their address bits share in common? Coming back from a pause, well, there's a total of 128 bytes here, same size as the cache, obviously. So their bottom 7 bits will vary, but the top 5 will stay the same. Let's call each group of 8 cache blocks one cache's worth of RAM, a cache block group. So there's one here, and there's another one there, and so on down the line. That's an unofficial term, by the way, cache block group. Now, our first cache block group has addresses running from all zeros to 5 zeros and 7 ones. Its top 5 bits are always 0, 0, 0, 0, 0. The next cache block group commences with address 0, 0, 0, 0, 1 and 7 zeros, and its top 5 bits are always going to be 0, 0, 0, 0, 1. We could say that the top 5 bits of the address identify the cache block group. Now, consider all the cache blocks that share the same home cache line. Like that one there, and then the next one, the first one in that group, and the first one in that group, and so on. All the cache blocks that share the same home cache line, how do their address bits vary, and what do they have in common? And the answer is the middle 3 bits between the top 5 and the bottom 4 identify the home cache line. So if we broke that up just a little bit, those middle 3 bits right there. As we advance from cache block to cache block within a cache block group, those 3 bits go from 0, 0, 0 to 1, 1, 1, identifying the home cache line that each cache block goes to. So all cache blocks that share the same cache line have the same middle 3 bits, but different top 5 bits, since they're all from different cache block groups. Now, summarizing, we can view a 12-bit address as 3 bit fields. 5 bits for the cache block group, 3 bits for the home cache line, and then a final 4 bits within the cache block or cache line. In the next segment, we'll look at how CPU knows which cache blocks are present in the cache, and we'll look at newer cache designs that reduce the competition between cache groups for the same cache line.